Delaware Tech, Chemistry 100, Chemistry 110, buffers. Buffers are solutions that resist changes in pH, especially when small amounts of acid or base are added to your solution. And there are two basic types of buffers, two ways to make them in general. You can start with a weak acid and add a certain amount of conjugate base, and these have to be in a specific ratio to get different pHs. And so an example of that would be acetic acid here, CH3CO2H. That H is the proton that would be released by the acid. And acetate, and that's CH3CO2 minus. But you can't buy just the acetate. You have to buy it as a salt of the conjugate base. For instance, sodium acetate shown here. You could also buy potassium acetate or ammonium acetate. As long as it's some form of acetate mixed with acetic acid, you can make a buffer from that. That would be called an acetate buffer. So it has to be a weak acid, however, and its conjugate base. You can also do it from a weak base and its conjugate acid. But again, you can't just buy the conjugate acid sometimes. In the case of ammonia shown here, NH3, the conjugate acid would be ammonium ion. And you can't just purchase ions. You have to purchase the salt of it. So ammonium chloride would be something you could buy. Ammonium bromide would be something else you could buy that has ammonium ions in it that could act as the conjugate acid of the weak base. So you always have to have a little bit of each in your mixture to have a buffer system. Buffers cannot be made with strong acids by themselves or strong bases, and certainly not with a strong acid and a strong base together. And the reason for that is if you mix a strong acid and a strong base, it goes completely to the right side of the equation, and there is no equilibrium. There's no balance between having a certain amount of the reactants and products at any one time. And you need to have a little bit of both in order for it to behave as a buffer. And here's the reason why. Here's an equilibrium with a theoretical acid, HA, and we're going to assume this acid is a weak acid. So a small amount would become A minus, its conjugate base. But you can always mix these in the laboratory. You can actually take a mixture of HA, the acid, and a store-bought sample of A minus, the conjugate base. So, for instance, you can buy the acetic acid and sodium acetate to provide your acetate. And when you put these two together in water, there will be an equilibrium set up between the two, and you always have some of the reactants on the left, the original acid, and you always have some of the reactants on the right, the conjugate base, as well as hydronium ion, in this case, with a weak base system, a weak acid system. And the reason why this is important is if you were to add a certain amount, a small amount of hydroxide, a base to your system, it will shift the equilibrium to the right to balance it out, but it won't dramatically shift it so far to the right that the whole equilibrium will be lost. That will only happen if you add an enormous amount of hydroxide to the reaction. Likewise, if you added acid in the form of hydronium ion or whatever acid that you put in water, which will turn into hydronium ion, it will shift the equilibrium to the left, but there will still be an equilibrium. So this equilibrium reaction absorbs the excess hydronium ion or the excess hydroxide ion so that a balance is made and the pH is relatively stabilized to a point. So buffers have to have a weak acid or a weak base in them, along with their respective conjugate. And you can either do that by adding the conjugate directly by buying the salt and mixing the acid with its conjugate base salt, or buying the weak base and mixing it with its conjugate acid salt. That's fine. You can do it that way. Or you could just start with, say, a weak acid or a weak base and then add something to turn part of it into its conjugate without turning all of it into the conjugate. So what do I mean by that? Well, let's start with just the regular way of making a buffer, starting with a weak acid and its conjugate base. Here is acetic acid shown in red, and potassium acetate, a salt of the acetate, the conjugate base. And you can mix those two together and you get a perfectly good buffer system that would stabilize its pH at a certain pH. Every buffer system has its own pH range that it works at. It's a fairly narrow range of only about 1 pH unit. In this case, these buffers with acetate and acetic acid tend to work well at stabilizing pHs between 4 and 5. You could have also made it using carbonic acid. Carbonic acid's conjugate base is bicarbonate, or otherwise known as hydrogen carbonate, HCO3-. Now, you can't just buy the ion by itself. You have to buy the salt. So you could buy sodium bicarbonate or sodium hydrogen carbonate, or you could buy the potassium salt as well and mix that with the carbonic acid, and you would get a perfectly good buffer system that would buffer at a different pH, actually at a significantly higher pH than acetic acid does. But there's another way to do this. You could start with your weak acid. Instead of buying the conjugate base salt and adding it in, you could just take a strong base like KOH, not a lot, less than the amount that you have of the acetic acid, and turn some of your acetic acid into acetate. In this case, it would turn into potassium acetate. And what would happen is you would lose some of your acid, you would create some of your conjugate base, the acetate, and you'd have a mixture between the two. And you could do the same thing with carbonic acid, add a small amount of a strong base, like sodium hydroxide, could have used the potassium hydroxide, and you'll end up creating some sodium bicarbonate or sodium hydrogen carbonate from your carbonic acid. And you'll end up with a little bit of each, the acid and its conjugate base. And that would work perfectly well. Likewise, you can do this with bases. If you start with a weak base, you could buy the salt of the conjugate acid. If I started with ammonia in blue, I could buy ammonium chloride, which would release ammonium to my solution, and I'd have a mixture of ammonia and ammonium, and that would make a perfectly good buffer system somewhere in the region of pH 9 to 10. I can do the same thing with another weak base. In this case, C5H6N is pyridine, and the conjugate acid of pyridine is called pyridinium ion. So you can't buy pyridinium ion all by itself, but you can buy pyridinium chloride. So if I mix a little bit of each of these, I would get a certain ratio, and I could make a buffer system that would be that would have its own pH. It would be a bit lower than the pH for ammonia, though. Likewise, I can make my own conjugate acid by adding a little bit of strong acid, like HCl, to my ammonia. So I will turn part of my ammonia into ammonium chloride and leaving some ammonia and also having some ammonium chloride, so I would get my mix of the two, and that would be a buffer system. Or I could take pyridinium, and instead of adding pyridinium chloride, for instance, I could add a little bit of HCl, a little bit of hydrochloric acid, turn part of my pyridine into pyridinium chloride, and then I would have a mix of two, and then these two would work perfectly well as a buffer system, just like the first set with pyridine would. So let's talk about the buffers that are important in your own body. Your blood has a very specific pH, pH 7.40, and it only varies by about 0.05 pH units, either up or down. So everybody's blood that's healthy has pH between 7.35 and 7.45. If you go outside of that range, you actually become quite sick and will die most likely if you're in extended periods outside of that range. So your body has to maintain the pH in your blood very carefully, very closely, at a very narrow range. And it has a number of systems for maintaining this pH. There are actually several systems. And one of them is the fact that hemoglobin is in your blood, and hemoglobin, believe it or not, has lots of groups on the protein itself that can act as buffers. So you have hemoglobin in your blood that acts as a buffer, and hemoglobin, of course, the main role of hemoglobin is to transport oxygen throughout the throughout your body inside the red blood cells. But a lot of people don't realize the hemoglobin itself acts as a buffer. All proteins can act as a buffer, but there's a lot of hemoglobin in blood, so there is a large, what we call, buffering capacity due to hemoglobin. It works very well to buffer, but it's not perfect. You also should know that CO2 is transported in your blood, in the plasma, in the red blood cells as well. And CO2, when it dissolves in water, becomes carbonic acid. CO2 will react with the H2O and literally form an acid, carbonic acid. So if you have excess amounts of CO2 in your blood, it will react to form H2CO3, this acid. And this is problematic. You don't want too much CO2 in your blood at any one time. A small amount is okay. A large amount will mean that your blood becomes very acidic because this acid will release protons, and that will be an acid. Of course, the better way to draw this would be to write it with water, so the proton is released to the water and you make hydronium ion, but that's the same thing. You end up producing acid because you have too much CO2 in your blood. And your body has ways of dealing with this. If you have too much CO2 in your blood, your brain will turn on mechanisms that will cause you to hyperventilate. You'll breathe harder and harder to release CO2 out of your lungs, which will help draw the CO2 out of the blood. And so what will happen is you will be exhaling the CO2 as a way to get rid of the CO2 that is in excess in your blood, making your blood too acidic. And if you have too little CO2 in your blood, and your blood is too basic, too alkaline, your body has ways of either keeping more CO2 in you, and one of those ways is to make you breathe less, what's called hypoventilating, or to excrete this other product that is in your blood as a result of this reaction, and that is the bicarbonate, the hydrogen carbonate ion. So your body can turn on, your brain can turn on mechanisms that allow the kidney to excrete excess amounts of bicarbonate, which will help draw this reaction further to make more bicarbonate, which will help make more CO2 be absorbed into your blood and become more of this acid. So that's another way you can compensate for it. But in the meantime, you have this buffering system that is created. You have a conjugate, you have your weak acid here, and its conjugate base is the bicarbonate, and the combination of these two in your blood helps buffer your blood as well. Now, it doesn't really buffer at the correct pH, but it does help maintain it by helping control the CO2 concentrations that are in your blood at any one time. And this becomes very important. And